Okay, so let's go ahead and now that we've built the model, let's go ahead and do some curve fitting for it. I'm going to choose to do curve fitting rather than answering questions because once we have the model, we can answer questions. It just basically comes down to some algebra. It's the curve fitting that I think is a little tougher thing to do. So we know this is Newton's law of cooling. So our formula again, our temperature at any time is the difference between my initial temperature and my surrounding temperature times e to the kt plus whatever my surrounding temperature is. All right, so we got to find all this data. We plug it in. We're good to go. So here's what we know. An alloy is pulled out of a smelter at 1,000 degrees Fahrenheit. So that sounds like T of 0 to me. Right? So the temperature of my alloy is 1,000 degrees Fahrenheit at the beginning. And again, if you want a data point, right, we're saying time equals to 0, temperature is 1,000. It's allowed to cool in a laboratory that has a room temperature of 105 degrees. So it must be somewhere here in Phoenix, right? So that's telling me that the surrounding temperature is 105. Okay, so we now know what the initial time is, and we know what the surrounding temperature is. After 5 minutes, the alloy has cooled to a temperature of 800. So we know one of my data points is 800. Find a function that models the situation. So really, you got it right here. I just plug and chug. So my model, right, is T of 0, which is 1,000, minus my surrounding temperature, which is 105, e to the kt, plus my surrounding temperature, which is 105 degrees. Right? And so cleaning this up at the moment, I believe if you subtract 105 from 1,000, you end up with a 895 e to the kt plus 105. All right, so there's our model at the moment. Of course, what's missing? We don't know what k is, right? And that is what that next data point is. We are basically saying that when you plug 5 in here, the value is going to be 800, right? So that's what that point is basically saying. So we got to find a k that when I plug a 5 into my function, the output's 800. So we basically solve for k using some algebra. So we'll subtract 105 from both sides first. That gives us 895 e to the 5k equals, and I believe we end up with 795 there. No, not 7. I better 695. All right, so we end up with 695 at this time. Divide both sides by 895. Right, we get that e to the 5k is whatever that funny fraction is, and I'll just go ahead and leave it the way it is. Take the natural log of both sides. We have 5k equals the natural log of that crazy fraction. Right, divide both sides by 5, and we get k is the natural log of that crazy fraction all over 5. All right, and so at this stage, I'll definitely reach over from my calculator to get kind of a decimal value out of that so we can use it. So the natural log of 695 divided by 895, and then we're going to divide that number by 5. And what we get is negative, how about we just call that 0506. So negative 0.0506. So there's your k. So our model then, right, at this, putting it all together, T of T is 895 e to the negative 0.0506 t plus 105. So there is the model for that alloy that's cooling in a room that's 105 degrees. All right, and so now that we have that model, I can answer any question that may come up, and in this case, there is a question, right? They want us to use your model to find how much time it will be needed for the alloy to reach 100 degrees Fahrenheit. Okay, and I think I got a typo here because it's only going to reach 105 degrees Fahrenheit, right? That's the surrounding temperature. So the way I have it written here, this can't be done. So how about I make this 100 and let's say 20. Okay, that way it's well defined, right? So hopefully you understand that. So I'm basically trying to find, right, what time value creates an output of 120 degrees. So basically that means that 895 e to the negative 0.0506 t plus 105 is equal to 120. And so we basically, the math's pretty similar, except now we're solving for t rather than k. So I'll subtract 105 from both sides, right? And what I get is 895 e to the negative 0.0506 t, right, equals 120 take away 105 is 15. Divide both sides by 895. We have e to the negative 0.0506 t equals the natural log of 15 over 895. And that will simplify, but I'll just leave it at that. Taking the natural log of both sides, oops, I already did that over there, right? That cancels that out, and we get negative 0.0506 t equals the natural log of 15 and 895. So t, if we divide that decimal out on both sides, is the natural log of 15, 895, all divided by 0.0506. So there's your exact value. All right, that way I know you got the algebra right. All right, and what's the estimated value? We'll reach for our calculator. So reaching for that, we got the natural log of 15 divided by 895. And then we're going to divide that by a negative 0.0506. So the time will be 80.81, right? And that is in minutes. So about an hour and 20 minutes, right? So an hour and like 21 minutes if we round off, right? That's how much time it's going to take for that alloy just sitting there by itself, all right, to reach 120 degrees according to our model. Right? Of course, if you've ever been in a manufacturing plant when they take an alloy out, things don't actually go the way that I portrayed them. Right? What they usually do is they temper the alloy and they put it in some cold water to really cause the temperature to drop drastically very fast. That hardens things, creates more characteristics in the steel. But now I'm getting into metallurgy, all right? And we just want to do the math at the moment. But there's your math. So what we have again is Newton's law of cooling. We got a formula, all right, to use. You plug in the information, and just like we have been doing with our curve fitting before, we use another data point to find our K value, all right? And then once we have our K value, we have our model. And then once we have our model, we can answer anything. I can, give me a time value. I can tell you the temperature. Tell me what temperature you want to be. I can find that. Whatever the case is, I got you covered. Right, so that wraps up 6.8. Those are our exponential equation situations. Like I said at the beginning here, there are many more. There's things going on in finance. Population models are actually what we call logistics curves. But we're getting tired. We're late in the semester. I'm just going to keep it at this nice, relatively simple, right? Exponential decay, exponential growth, and Newton's law of cooling examples. We'll keep it that simple, learn from there. And as you guys move through your math careers, your science careers, you'll learn more. At least you have the basics. If you have questions, please sure you ask. Jump on Canvas and ask them there. Show me your work. Give me an opportunity to grade it and give you feedback. Or see me during an office hour. Whatever it takes to help you learn the material. Finish strong. We're almost done.